In this section, we're going to take a look at tangent planes and normal lines. Before we begin this section, let's motivate a little something that we're going to be using. Consider a function of two variables. And here, let's be specific. Let's keep it simple. Let's say I have f of x comma y is equal to x squared plus y squared. Okay? Now, this is a function of two variables. We can consider level curves of this, though. We can say something like, okay, let's consider the level curve where z, which is equal to f of x comma y, is equal to a constant number. Let's say, for example, it's equal to the number 4. Okay, well, that is a level curve of our function. Now, note that our function is a function in space. You have the domain is on the plane, and you have a third variable that is determined by these points on the plane. You have z equals f of x comma y. However, here we can consider this as a single plane, as a single level curve on the plane. And here that would be a circle of radius 4. A circle of radius 2. Okay. Well, okay, but couldn't we also think of that backwards? Couldn't we also say, all right, I know this is y, x squared plus y squared equals to 4. That's the equation of a circle on the plane. But couldn't I think of this as being a level curve of a surface? Right? You can say, okay, I have a surface, and I can think of that as being a curve on the plane. But you could also go backwards. You could say, okay, well, here I have x squared plus y squared equals to 4. And I could think of this as being a level curve of a bigger surface. So you can go back and forth. You can think of, okay, this is in 3 dimensions, but a level curve is in 2 dimensions. Oh, well, here I have a curve in 2 dimensions. I could think of this as being a specific level curve of something in 3 dimensions. We can extend that even higher. Let's say we started with something in 2 dimensions and said, okay, what if, in 3 dimensions, and we said, okay, what if we wanted this to be a level curve? What if, instead of saying, okay, I have my function is a function of 2 variables, z equals f of x, y, what if that itself was a level curve? Well, then we could take that and think of it as a level curve of something even higher in dimension. So note, for this section, that's what we want to do. In this section, we will consider, let's just say we will write z equals f of x comma y as, we're going to take our z and subtract it over this way. So we're going to write that as 0 equals f of x comma y minus z. Oh, but if you notice, that's a function of 2 variables. Oh, no, it's not. It's a function of 3 variables. And that function of 3 variables is equal to a constant. Oh, so then this would be a level curve of a function of 3 variables. And so we will consider this the level curve of a function, I guess I'll call it capital F, of x comma y comma z. You say, well, what does that gain us? Well, one thing it gains us is, if this is a single function of 3 variables, then we can talk about the gradient of this function in 3 variables. You say, well, couldn't we do the same thing for the function of 2 variables? Well, we can, but now it's going to have a much more, shall we say, involved meaning. All right, so instead of speaking in vague terms, let's go ahead and develop some stuff which will lead to a definition and a theorem. Let's see where this takes us. Let's begin with, let's take a surface S. So let S, and here I'll label this as a surface, It's one of these things. It's a z equals f of x comma y. Let a surface S be written as f of x comma y comma z equal to 0. So in other words, take one of these, move that over, and then call that thing capital F of x comma y comma z. Okay? Now let x naught comma y naught comma z naught be a point on that surface S. So here I'll call this P for point. Let P equal that point be a point on the surface S. Now, let C be a curve. That's somewhere on the surface S and that crosses through the point P. Let's go ahead and define that. Be defined by, and we'll give the, we'll call C a, we'll give that by a vector valued function, r of t equals. Now remember, this curve is on this surface which is in space. So we're going to give it a parameterization in space. That's going to be x of t I plus y of t j plus z of t k. Note, since C is on this surface, then it must also satisfy these conditions, that f of x comma y comma z must equal to 0. So that means that f of x, and here x is a function of t, x of t comma y of t comma z of t must equal to 0 for all values of t. Right? Because it exists on this curve C is on the surface, so it must satisfy all the conditions of the surface. All right. Now, if f is differentiable, and all of our derivatives exist, x prime of t, y prime of t, and z prime of t exist. Remember, these are functions of a single variable, so we mean they're differentiable in the Cal 1 sense. If all of these exist, then, and this is by the chain rule, we know that f prime of t is equal to f sub x at x comma y comma z times x prime of t plus f sub y at x comma y comma z y prime of t plus f sub z at x comma y comma z z prime of t. All right? By the chain rule, if you're taking the derivative of f, you take the derivative of the components of f times the partials of f. F partial x, f sub x times x prime plus f sub y, y prime. Oh, but this is a function of 3 variables. Okay, so f sub z times z prime. Like that. But note that since f is equal to 0 for all t, then it's a constant. And the derivative of a constant must be 0. Since f of t is equal to 0 for all t, then f prime of t must equal to 0 for all t. Oh, so then that means that this is equal to 0. That's f sub x at x comma y comma z times x prime of t plus f sub y at x comma y comma z y prime plus f sub z at x comma y comma z times z prime of t must equal to 0. But notice what this is. This is the gradient of capital F, and x prime, y prime, and z prime, those are the derivatives of the components of R. Oh, so this is the gradient of F dot the derivative of R. So this is gradient of F at x comma y comma z dot the derivative of R with respect to t. Must equal to 0. Oh, okay. But now the dot product of these two vectors is 0. So these must be orthogonal. So the gradient of f at x comma y comma z must be orthogonal to, well, to what? Well, to r prime. Well, what do you mean by r prime? Well, it's the derivative of r. Yeah, but physically, what does that mean? Oh, well, those would be the lines that are tangent to r at that particular point. But notice, we said that's for all t, for any value. It doesn't matter which way we're going. So it's orthogonal to all tangent planes. To all tangent lines, rather. To all tangent lines, meaning in all directions. At the point, we call it P, right? At the point P. And at the same time, it gives us the set of all tangent lines. Why? Well, because if we have a line that's perpendicular, that's orthogonal to all of them, then that's the line that's normal to the plane, which defines our plane, as we saw back in chapter 11. If you know the vector that's orthogonal to a plane, that means you know everything you need to know about that plane. So this brings us to a definition that's motivated by this concept up here. Let f of x comma y comma z be differentiable, a function that's differentiable at the point x naught comma y naught comma z naught. Let's call that P. Okay, so let f be differentiable at a point P, which we'll call x naught comma y naught comma z naught, on a surface S. That's given by this earlier adaptation, where we take a typical surface, subtract this over, and instead of considering it as a surface, we consider it as the level curve of a function of 3 variables. So where S is given by f of x comma y comma z equals to 0, such that, and here we have a condition on f, we need such that the gradient of f at that point, x naught comma y naught comma z naught, is not identically the 0 vector. Then, the plane that is normal to the gradient of f at x naught comma y naught comma z naught is called the tangent plane. To S at P. And the line through the plane in the direction of the gradient. The line through that plane in the direction of the gradient f at x naught comma y naught comma z naught is the normal line to S at P. The normal line to S at P. All right, as a quick visual. We saw in previous sections that the gradient, among other things, gives us the line that is, it gives us a vector that is orthogonal to the line that is tangent to a level curve. So if I have a collection of level curves, like this, and I have a point that's on one of those level curves, the gradient gives me a vector. Okay, that vector is orthogonal to the line that is tangent to the curve. Okay, and the reason that works is because you can compute the gradient. You can find this vector. Okay, well, what if I wanted something in a greater dimension? What if I had, for example, instead of a circle, let's say I had a sphere. Okay, well, I want something tangent to this circle, say, for example, at this point. Well, okay, but it's this is in space, right? On the plane, something that's tangent to the circle on the plane is a line. Over here, this is in space. Something that's tangent to the circle, I would have lines in a bunch of different directions. I'd have a line this way, and a line this way, and a line this way, and a line this way. There's lots of lines that are tangent to that point. Oh, okay, so then that defines an entire plane. So we no longer have tangent lines, now we have tangent planes. Okay, well, I need something that defines this plane. Well, the gradient is tangent to this. This is just a three-dimensional version of that. We're saying, okay, if you can find the gradient of your function, then it'll give you a vector that's normal to all of the vectors on this plane, and therefore it defines this plane. Oh, but this vector needs to be in 3 space, right? It needs to be in a space of 3 dimensions. Oh, so then I need a gradient of a function that has 3 variables. Okay, so then it's not really sufficient for me to start off with z equals to f of xy, because the gradient of this would be on the plane. I don't want something on the plane. I want something in space. That way I can define this plane. Okay, so I can't use the gradient of this. Oh, but if I move this over, I can go ahead and consider this the level curve of a function in 3 dimensions. So this surface is no longer a surface in its own right. Rather, it's the level curve of something in 3 dimensions. To put this a bit more succinctly, thinking of this as a surface makes it hard, makes it difficult to work with. But treating this as the level curve of a 4th dimensional object, oh, I just compute the gradient, and that's all I need to worry about. Because once I have the gradient, I can use the properties from the previous section to then confirm that this is orthogonal to every line that's tangent at this point, and therefore is orthogonal to the plane. Oh, but that must mean that that's the normal vector. That's the vector that's normal to the plane and therefore defines the plane, as we see in chapter 11. All right, so now this brings us to a theorem. Once we define what this is, and incidentally in this illustration, this would be the plane tangent to the surface. So this right here will be the plane tangent to the surface. Let's call this sphere, we'll call it the surface S. So this would be the plane tangent to S at that point. X naught comma y naught comma z naught. And then this line that is normal to that plane, That's what we defined as the normal line. If it's normal to the tangent plane, we just go ahead and say it's normal to the surface at that point. All right, so that brings us to a theorem. I don't care what anybody heard, I'm not dropping things. All right, here we go. Theorem. Let's begin with one of those things, right? Let f of x comma y comma z be differentiable at some point x naught comma y naught comma z naught. Then the equation of the tangent plane to the surface given by f of x comma y comma z equals 0 at x naught comma y naught comma z naught is given by f sub x at x naught comma y naught comma z naught times x minus x naught plus f sub y at x naught comma y naught comma z naught times y minus y naught. Why? Oh, why not? Plus f sub z of x comma y, x naught comma y naught comma z naught times z minus z naught is equal to 0. So I guess I'll put it on this side, is equal to 0. Which is nice, because that means all we have to do is be able to compute our gradient, and there it is. That'll give us the coefficients that we need to find the tangent plane. The proof of this really does just take us back to what we use to define a plane. X naught comma y naught comma z naught is on the plane. Clearly, right? If you have a plane that's tangent to the surface at that point, that's the one and only point where we're guaranteed that the surface and the plane share. So clearly that is on the plane, because it's the only point that we can guarantee is on both the plane and the surface. Okay, it's clearly on the plane tangent to S. Tangent to the surface. Okay, let's let x naught, let's see. Well, no, we already have that one. So let's just call this x, y, and z. So let x, y, and z define some other point that is on the tangent plane. It's not going to be that one. It's just some other point somewhere out here. Define some arbitrary. Doesn't have to be any specific point. Just arbitrary is fine. Arbitrary. There we go. Helps if I learn to spell. Some arbitrary point on the plane. Other than the one we started with. Well, then every vector on this plane will be the difference between this arbitrary point and the one point you're sure is on there. Basically, every vector can be written as from here to here, from here to here, from here to here. It can be written from the point x naught comma y naught comma z naught to that other point, whatever it might be. So every vector of the type v equals to x minus x naught I plus y minus y naught j plus z minus z naught k is on that tangent plane. But now, since the gradient of capital F at x naught comma y naught comma z naught is orthogonal to every vector that's on the plane, to every vector on the tangent plane, well, then we can define that tangent plane by saying we want all vectors v such that f at x naught comma y naught comma z naught, or sorry, the gradient of f at x naught comma y naught comma z naught, dotted with v is equal to 0. Which implies that, well, if we want the gradient is f sub x comma f sub y comma f sub z. And if we're dotting that with v, that'll be f sub x times x minus x naught plus, you're going to have this partial with respect to y times this expression here. So it'll be f sub y x naught comma y naught comma z naught times y minus y naught plus z minus z naught times the partial with respect to z. F sub z of x naught comma y naught comma z naught times z minus z naught is equal to 0. I ran out of space, so I'll write the 0 over here, which is our result. 0 is equal to f sub x times x minus x naught plus f sub y times y minus y naught plus f sub z times z minus z naught. And that concludes our proof. This is actually really pretty efficient. By considering this surface as the level curve of something in 4 dimensions, you can quickly find every vector that's tangent to that point in every direction by just finding the gradient in that 4th dimension. So let's consider some examples of this. First of all, let's go ahead and find the equation. Or I guess I should say find an equation. These are not unique. After all, you can multiply anything by a scalar multiple and still have it give you the same vectors. So find an equation of a normal vector to a surface given by x squared plus 3y plus z cubed equals 9 at the point 2 comma negative 1 comma 2. Okay. So here we're not going to look for the full plane, just the normal vector. All right, so here you have a function of x and y and z. Here f of x comma y comma z is equal to, here you should move everything over to this side. Note here that's a constant, so it won't really make a difference. But in other cases, it may be written as x squared plus 3y equals 9 minus z cubed or something of that nature. So always have everything over on one side, and the other side should be 0. as we see here at the beginning. Note in this section we'll write all of our surfaces as 0 equals everything else. All right, so here let's go ahead and write our f of x comma y comma z as x squared plus 3y plus z cubed minus 9 equals to 0. All right, so f of x comma y comma z equals that, which is equal to 0. All right, so, and again, because that's a constant, it won't really make a difference in this computation, but should it be variable, well, then it will. So now we want to go ahead and find the gradient of f at x comma y comma z, and that's, well, that's not too bad. The derivative with respect to x of all of this is constant, so the derivative will just be 0, and really I just have to worry about this part. So that'll be 2x, comma, let's see, the derivative with respect to y, all of these will be 0, leaving me just this part. So that's just the derivative of 3y is just 3. And then with respect to z, this and this are all constants, so all I have to worry about is the derivative of this one. Z cubed will give me 3z squared for a derivative. Okay. So now we want to go ahead and find that gradient at that particular point. So gradient of f at 2 minus 1, 2. And so now we can go ahead and take those values and substitute into this gradient to get our result. So that'll be 2 times 2, I think it was 4. That's a constant 3, so it doesn't matter what we're plugging in, so we'll leave that as a 3. And here for z, we're plugging in 2, so that'll be 2 squared is 4 times 3 will give us 12. Okay. So there's our gradient like that. Note that, again, this is not unique. This gradient is a vector that's normal to the surface. If I took this and scaled it by a factor of 2, it would be a different vector, but it would still be in the same direction, and therefore still would be normal to the surface. If I multiply this by 1/2 or 2/8, or I'm not sure why I didn't say 1/4 there, but whatever. It doesn't matter what number I multiply by. If I multiply by any non-zero number, I'm still going to get a vector that's normal. So here, that's just, I wrote an equation of a normal vector. I guess I should just have a normal vector, right? It's not really an equation. Find a normal vector. There you go. Find a normal vector to the surface. If any scalar multiple will work, there is often utility in having a unit normal vector. So here's a follow-up. Let's go ahead and find the unit normal vector. Sometimes you only care about the direction and you wish to not have the magnitude of the vector affect anything. So oftentimes a unit normal vector will be used for things. And in that case, you would simply take this, find its magnitude, and scale it down. So let's see, the magnitude of the gradient of f at 2, -1, 2. That's equal to the square root of, let's see, that's going to be 4 squared plus 3 squared plus 12 squared. And that's a square root of, let's see, 16 plus 9 is 25. Plus 144 is 169. So the square root of 169 will give us 13. So that means that the unit normal vector that we want, I'll call it n for normal, is equal to, I will take my gradient and divide by its magnitude. So that'll be 4/13, comma 3/13, 12/13. And again, both of these are normal to the surface at that point. However, here this is a unit normal vector. Right? Both of them are normal. However, we'll often have need for a unit normal vector in coming problems. Go ahead and give this a try. Go ahead and find the equation of the plane. Once you have the normal vector at that point, then it's simply a matter of putting that into this form over here, where that's those components of the gradient, and here we simply have x minus x naught, y minus y naught, and z minus z naught. Don't forget, all of that is equal to 0. So go ahead and give this a try. Find the equation, and this time it is an equation. Oh, I think that's why I wrote find an equation of here. I think I was mixing the two questions. So here, find an equation. And it should be an equation because, again, we can have different normal vectors, which means we can have different looking equations, which all give the same thing. So find an equation of the plane tangent to 8 equals xy squared plus 3x minus z squared at the point 1, negative 3, 2. All right, go ahead and give that a try. First, start by finding a normal vector. You don't need the unit normal vector. Any normal vector will suffice. And then putting that into this form. Don't forget, in the end, the equation should be this all is equal to 0. Go ahead and pause the video, give yourself the time you need, and once you're done, go ahead and unpause and we'll go through it together. All right, here let me go ahead and correct this to an, right? It should be find an equation. All right, so if you end up with a scalar multiple of what I end up, that is still acceptable. Okay, so here we go. We want to first of all find the gradient of our function. Oh, actually, first of all, we should write our function, right? F of x, y, z is equal to, we want one side to be 0. Again, this one is a constant, but if it was not constant, well, then you'd end up having a different function. So always make sure one side is equal to 0 first. Xy squared plus 3x minus z squared minus 8. Okay, so there we go. And that all would be equal to 0. So now if we take the gradient of this function of 3 variables, we end up with, all right, with respect to x, the derivative is y squared plus 3. So that would be our first component. With respect to y, notice there is no y here, so that would be 0, right? Oh, wait, no, there's a y right there. I must need new glasses. So here, if I take the derivative with respect to y right here, that would give us 2xy. And then if I take the derivative with respect to z, well, there you go, that's minus z squared. So I'll take the derivative, that will give me minus 2z. And here, the derivative of this constant would be 0 for all of them. So in any event, there's my gradient. All right, well, now I want my gradient specifically at this point. Okay, so let's find the gradient of f at 1, negative 3, 2. All right, well, that's going to be, well, let's see, y is equal to negative 3. So negative 3 squared is positive 9, plus 3 will give us 12. Okay, here we'd have x is 1 and y is negative 3. So 2 times 1 times negative 3 is a negative 6. And since z is equal to 2, negative 2 times z, well, negative 2 times 2 would give us negative 4. So there is our gradient, which gives us a vector that is normal to the plane at this point. Note, if you have any scalar multiple of this, that is also correct. If you have this with negative 12, positive 6, and positive 4, that's fine, because of course that's a scalar multiple by negative 1. If you divide all of these by 2, so that I get 6, negative 3, and negative 2, that's fine. Any scalar multiple of this one is correct. Unless there's some reason why we specifically want, say, a unit normal vector, really any normal vector will suffice. Okay, so then that means that our tangent plane is going to be given by the gradient of f at that point, which is 1, negative 3, 2, dotted with the vector, the x minus our x value, comma, y minus our y value. So that's minus a negative 3. That's y plus 3. And then z minus our z value, z minus 2. And so that's going to give us 12 times x minus 1 minus 6 times x plus 3 and minus 4 times z minus 2. Okay. So then that means that the equation that we want is going to be 12 times x minus 1 minus 6x plus 3 minus 4z minus 2 is equal to 0. And that'll give us one version of the equation of the plane that is tangent to this surface at this point. Note that oftentimes you will distribute these. So you can write this as 12x minus 6, oh, there should be a y there, shouldn't it? Minus 6y minus 4z. And then this would be what? Minus 12 minus 18, which is a minus 30, plus 8, which is a negative 22. So you could write this as this. So that would be another acceptable way to write this. You might notice that all of these are even numbers, including 0. So you divide everything by 2. So you might also write 6x minus 3y minus 2z minus 11 is equal to 0. So that would also be correct. And as I mentioned, any scalar multiple of this would be fine. All right. For our next example, let's take a look at something slightly different. It's still going to work pretty much the same way, but there is a slight variation, which at first may not seem obvious. Let's go ahead and find the equation. And here, I'm going to go ahead and use the symmetric equations. Find the equation of the line that is tangent to the intersection of the two surfaces. They're given by, the first surface is going to be given by x squared plus y squared plus z squared minus 14 equals to 0. So here we already have it as a function of f of x, y, z equals to 0. And then the second equation, the second surface is going to be given by x minus y minus z equals to 0. And again, that's already written as a function of x, y, z equals to 0 at the point 3, 1, 2. All right. You might say, all right, well, how are we using what we just saw for this? Before we were looking for an equation of a plane that was tangent. Oh, well, okay, if it's a line that's tangent, that exists on the tangent plane, I suppose. But well, the tangent plane of which one? Well, it would have to be both of them, wouldn't it? Because after all, if we want the intersection of these surfaces, what we're saying is, okay, here's the surface. And here's another surface. And of course, I'm drawing the same surface every time because it's really the only one I can reliably draw. Okay? So let's say that we want to find the line that's tangent to the intersection at this particular point. Okay, well, if I find the plane that's tangent to the surface on the left, that'll be this one. And that'll include every line that's tangent to the surface at that point, in every direction. Oh, but if I find the plane that's tangent to the surface on the right, well, that'll be a different plane. Okay, but, well, that will also possess all the lines that are tangent to the surface at that point. Well, then there's got to be one line, since they're overlapping here, there's got to be one line where it exists on both of those planes. Right? So what we need to do is we need to find some line that is on both tangent planes. Okay, well, in order to define the tangent planes, let's go ahead and define their normal vectors. That's the easiest way to define a plane anyway. All right, so let's go ahead and do that first. Let's find the vector that's normal to surface 1 at 3, 1, 2. Okay, well, we know how to do that. We're going to find the gradient and plug in that point. All right, so gradient of, and I'll call this one F1. Because, well, I'm going to do that again, so I'll call the next one F2. All right, so gradient of F1 at x, y, z, well, that's going to be 2x, 2y, 2z. This one's a constant with respect to all variables. So here the gradient is simply 2x, 2y, 2z. Oh, so at that point, the gradient of F1 is going to equal to 2 times 3, which is 6, 2 times 1, which is 2, and 2 times 2, which is 4. All right, so there is the vector that is normal to the first surface. Okay, so we have something that's coming out this way. Okay, now I can do the same thing for the second surface. Let's go and find the vector that is normal to surface number 2. Again, at that same point, 3, 1, 2. Okay, well then that's the gradient of F2. Okay, well the gradient, we're going to take the derivative with respect to x of this function here. Oh, well, that'll be just 1. And then with respect to y, well, that would be minus 1. And with respect to z, well, that's also minus 1. That's a vector. And then if we want to find the gradient of F2 at the point 3, 1, 2, well, it's still 1, minus 1, and minus 1. Because after all, that's a constant vector. There's no variables. There's nowhere for me to plug that in. So it's going to stay 1, minus 1, minus 1, like that. Okay, so now what I've done is I found the vector that's normal to the surface at that point going this way. Okay, but we don't want either of those. What we want is we want the one line that is on both of those tangent planes. Okay, well, if it's on the red tangent plane, it must be orthogonal to this red normal vector. If it's on the green plane, it must be orthogonal to the green normal vector. So what I want is I want something that's orthogonal to both these two vectors. Oh, that's their cross product. If you go back to chapter 11, that is the cross product. The cross product of two vectors gives you a vector that's orthogonal to both. So the line that is orthogonal to both of those vectors, which is really gradient of F1 at 3, 1, 2, and the gradient of F2 at 3, 1, 2, is the direction vector for the line tangent to their intersections. The line orthogonal to both of those gradients is the direction vector for the line tangent to the intersections of the surfaces that we're considering. All right, so let's find the cross product of those. Gradient of F1 at 3, 1, 2 cross the gradient of F2 2 at 3 comma 1 comma 2. That's equal to the cross product of 6, 2, 4 with 1 minus 1 minus 1. And that's going to equal to, well, let's see, I, J, K, I, J, K. Let's see, 6, 2, 4. And 1 minus 1 minus 1. So that would be negative 2i plus 4j minus 6k minus, going back this way, that would be negative 4i, negative 6j, and positive 2k. And when you subtract those, you end up with negative 2 plus 4. That'll give us positive 2i. 4 minus a minus 6. That's going to give us 10j. And negative 6 minus 2 will give us negative 8k. So here, the cross product of those two is going to be 2, 10, and minus 8. Oops. So now that we have the direction vector, we have a single point that's on the line, because of course we know we want the line that's tangent at that point. So now remember how you write the equation of a line. Recall the equation of a line, or rather the symmetric equations, right? There's more than one way to write it. So here I'm going to say the symmetric equations. Look like x minus x naught over a equals y minus y naught over b equals z minus z naught over c, where a, b, and c are simply the direction numbers, the numbers in your direction vector. So we have what we need. Here this will give us x minus, well, we know our x value is going to be 3, so it's going to be x minus 3 over 2 equals, let's see, y minus 1, since that second component is 1, right? Y minus 1 over 10, and that's equal to z minus 2, because again, that's our third component, 3, 1, 2, 3, 1, 2, over 2, 10, and minus 8. And there we go. One thing to note is, just like in the previous example, these vectors are giving us a direction, which means that any vector in this direction would work as well. So if you give me a scalar multiple of this, that will also be fine. So if, for example, you went ahead and multiplied this by 1/2, well, then that would give me 1, 5, and negative 4. That would also be fine. 1, 5, and negative 4. Notice that only changes your denominators, not your numerators. Your numerators are determined by the point that you know happens to be on your line. Your denominators are given by the direction numbers given by these components of your direction vector. If you multiply this by 7, well then 14, 70, and negative 56. And that would also be fine. Any scalar multiple of this works as a direction vector, so really any of these would be fine. Okay, finally, our last example for something like this. Let's go ahead and talk about angles of inclination. Let's go ahead and find the angle of inclination which we'll call phi, of the plane tangent to 2xy minus z cubed equals 0. So again, here we have a surface defined as a function of 3 variables is equal to 0 at the point 2, 2, 2. Okay, first a little word on what we mean by that. Whenever we have angles of inclination, we call them phi. That's an angle of deviation from this vector here, going straight up. So if you're going straight up this way, then your angle would be 0. If you're going in the direction of x or y, well, then your angle would be 90 degrees. Like that, right? So it's an angle of inclination is from the positive half of the z-axis. How far down are you from there? Okay, but now the question remains, how do you do that for a plane? Right? If I have a line, okay, sure, I can find the angle between that line and the z-axis. But a plane is more than just one line. And in fact, it's a lot of lines going in lots of different directions. Well, that's true. But there is a single line that describes the entire plane, and that's the line that's normal to the plane. So this is basically just another example of what we were talking about. Here, yeah, I'm talking about an entire plane, but that entire plane can be described using just its normal vector. And so when we talk about the angle of inclination of a plane, really we're talking about the angle of inclination of that normal vector. Because we can't talk about it with respect to the vectors on the plane. They're going in too many different directions. But this one summarizes all of them. So the angle that we want is really this one, from the positive half of the z-axis to this normal vector. All right, so first of all, let's find the normal vector. Then we'll worry about finding the angle there. All right, well, given our previous theorems, finding the normal vector is just finding the gradient at that point. So let's see, f at x comma y comma z is equal to 2xy minus z cubed. And so the gradient of f at x comma y comma z is equal to the vector. We're going to take the derivative with respect to x, which is 2y, comma the derivative with respect to y, which is 2x, comma the derivative with respect to z, which is minus 3z squared. Okay, well, that's the gradient, but we want it specifically at that point. Okay, so then the gradient of f at 2, 2, 2 is equal to, let's see, well, all my variables are equal to 2 now. So 2 times 2 is 4, 2 times 2 is 4, and 2 squared is 4 times negative 3 is negative 12. Okay? So there is our gradient vector, which means that is the vector normal to the plane that's tangent to our surface. All right, so that vector there would be what, 4, 4, negative 12. Like that. All right, so now we need to find this angle in between here. For this, we're going to go ahead and recall something from the beginning of the course, going back to chapter 11. Recall that the cosine of the, so let's see, let u and v be vectors, and theta be the angle between u and v. Then the cosine of the angle theta is equal to the dot product of u and v. We take the absolute values there, divided by the magnitude of each of those multiplied together. Okay. All right, well here, what do we want to do? We want to find the angle in between these two vectors. Okay, well that's the vector 4, 4, negative 12. This is the vector that points straight up. Oh, so that's the vector 0, 0, 1 in the direction of z. So here what I want is the angle. What I want is the angle theta, phi, I guess, the angle phi between 4, 4, negative 12 And the vector pointing straight up, that's 0, 0, 1. Okay, so then I know the cosine of, I probably should have just written that as phi from the beginning because now I keep getting confused. There we go. The cosine of phi, because that's what I defined as phi there, the cosine of phi is equal to the absolute value of their dot products divided by the product of their magnitudes. All right, well, let's see. If I multiply these, that's going to be 0 plus 0 plus negative 12. Well, that's the absolute value of negative 12, or in other words, just the number 12. Here, the magnitude of this one, well, it's a unit vector, so its magnitude is 1. And then the magnitude of this one, oh, let's see here. Let's do this off to the side. That would be the square root of 4 squared plus 4 squared plus 12 squared. So that's what? 144 plus 16 plus another 16, which is 176. All right, so that gives us 170. Oh, I suppose that can be simplified, right? That's 16 times 11. And that's 4 root 11. Okay, so that's going to give us our denominator, 4 root 11 times 1. So that's just sort of side work there. So that's going to equal to, here 4 goes into 12 3 times. So that'll be 3 over root 11. That times 1 doesn't really change much of anything. So that means that the cosine of phi, I finally said it right, is equal to 3 over root 11, which means that phi, the angle that we're looking for, is going to be the arc cosine, or the inverse cosine, whichever language you prefer, of 3 over root 11. Or if you prefer, you can always rationalize that, and you get phi is equal to the inverse cosine of 3 root 11 over 11. So here that would be our result. If you really, really have a strong inclination to write this as an angle, okay, you can type that into a calculator, but this would be the correct answer there. I suppose if you really, really wanted to, you grab one of these things. Mine's in degrees currently, so you could write that as, let's see here, 3 divided by root 11. Take the arc cosine. Let's see, is that right? Yeah. So if you really, really wanted to do that as an angle, you could write that as 25.2394 degrees. Or if you want to do it in radians, that would be, what, 3 divided by root 11. Oh, let's change that to radians. And then we take the arc cosine of that. And that would give us approximately 0.4405 radians. So any of those would be fine. This would be your precise, your exact answer. All right, so this is our angle of inclination. So over here, I went ahead and defined that as the angle from the positive half of the z-axis down around this way. You can also define it in a way that makes, actually the word makes a little more sense if you define it another way, although they are equivalent. As you're moving this way, your plane is being tipped in one direction or another. Okay, well, if your angle is 0, what does that look like? Okay, well, if my normal vector is got an angle 0 from the positive half of the z-axis, well, then that means that my plane is perfectly flat, meaning it's parallel to the xy plane. Okay, so then from the xy plane, you haven't lifted it at all. So there's no angle of inclination there. So you can think of the angle of inclination as being the angle that you lift up from the xy plane, or you can think of it as the angle from which you're deviating from the positive half of the z-axis. Notice as this one tilts, so does this one. As this one tilts this way, again, so does this one. All right? These are attached. So as I tilt this over, the whole plane tilts as well. So here the angle, you can think of that as, okay, I have this angle here, or if you prefer, you have this angle here from how far it deviates from the XY plane. If you think of it that way, it actually makes a little more sense in terms of the name. Your inclination, like an inclined plane, like a ramp, how much of a incline does your ramp have? So either of those is fine, which way you want to think about it. Either way, the computation works the same. All right, finally, we have one last theorem. We're not going to prove this one. We're not going to go very much into detail, nor are we even going to see any examples. Here, this theorem is entirely for comparison purposes, so you can compare with what we've just seen throughout this section. So, theorem. Let f of x comma y comma z be differentiable at some point x naught comma y naught comma z naught, and let the gradient of f at x naught comma y naught comma z naught be non-zero. Anything other than 0. Oh, that should be a 0 vector. Here we go. Then the gradient of f at x naught comma y naught comma z naught is normal to the surface through x naught comma y naught comma z naught is equal to the is normal to the surface. Is normal to the level surface. Through that point. Now compare that to the theorem that we saw in a previous section, in fact the previous section, which says that compared to the gradient of f at x naught comma y naught is normal to the level curve of f of x comma y through x naught comma y naught, or f of x naught comma y naught. And this essentially shows that everything we see in this section is just an extension of what we see when we first introduce the gradient of a function of two variables. The gradient is a vector in the plane. Now that we're in this section looking at functions of three variables, then our gradient is a vector in space. But just when you compare the relationship between the vector that the gradient gives us in the plane to the level curves, that's the same relationship that we get when we compare the relationship between the gradient of a function of three variables and the level surfaces, right? Versus this one here. So this one is going to be stated without proof. It's just for the sake of comparison to show that what we have seen in surfaces in space and gradients on the plane does extend into higher dimensions, with exactly the same properties. And that brings us to the end of this section. Should anybody have any questions, comments, or problems, please make a note of those and reach out to me at your earliest convenience. And I hope everyone has a nice day.